So in today's class, we are going to study what is the concept case hardening. Now, heating, soaking, and quenching. This will make part thoroughly hard. There are many applications where you don't require thorough hardness. Means, for example, if you take the case of gears, cams, and similar applications, you require surface hard and the center part must be tough for absorbing the shocks. So gear teeth are meshing. So inside part, core part of gear need not to be made hard thoroughly. So whenever gears are moving, whenever cam and follower are moving, a kind of shock, a kind of impact they have to absorb. The purpose is that the wear and tear of the surface or teeth of the gear must be avoided. For that purpose, the teeth of gear and surface of cam can be made hard only by keeping the center part or core part tough for absorbing the shocks. Many times there is some reciprocating mechanism where you have some table and and because of that reciprocation, there may be wear and tear of that surface. So the size of table is very large. Part is moving only along the surface. So whether I should make complete table hard? No, only the area where it is reciprocating, where the parts are meshing, that is supposed to be made hard. Then it is called as the special requirement where you need to hard only hello. Well, please reply somebody. Am I audible? Hello.
Yes, sir. Yes, sir. You are audible.
Yes, sir.
For 1 minute, it was I was out of the meeting due to network problem. Okay, I will repeat the statement once again. As per the particular requirement, as per the application, we need to make only surface hard. We don't want to make part thoroughly hard. Now, whether only making surface hard is cheaper process than making the part thoroughly hard. Cheaper means cost, with respect to cost. Definitely yes. If you take this component and you want to make it thoroughly hard, you have to heat in the austenitic zone. Depends upon size of the component. You have to wait till from surface to center, everywhere there will be FCC structure, that is austenite. Means soaking requires holding period at higher temperature, maybe 900 degrees Celsius. And then quenching complete part. And again you are coming across the cracks, etc. No doubt, your complete part becomes hard. But I am not interested. Only surface is coming under meshing area and remaining part of no use, it is just stationary. What is used to make the part completely hard? And second thing, cost of cycle will be definitely more. Making part thoroughly hard, it requires heating the part at higher temperature for long period by holding there. Heating cost, electricity cost, if it is electrical furnace, definitely it will be higher. So surface hardening and case hardening are the special requirements where you are supposed to make only surface hard up to certain depth. That's what is called as case hardening also. And best applications I told, that is cam, gears, and similar applications, and some of the meshing surfaces in case of reciprocal motion. For example, your lathe machine bed, you are moving the tailstock over it. You have seen. Just simple example I have told. In the same way, that tailstock we are not moving every time, but there are many applications where you used to move the part at the upper or upper surface, and remaining body part will remain stationary. So in that case, that surface slot or area must be hardened or must be wear resistant to avoid the wear and resistance. So such a process of making the surface hard or up to achieve the hardness up to certain case depth is called as case hardening or surface hardening. There are number of types. Few types we will study in today's lecture. Previous class I told Jomini and quench method and Grossman's critical diameter method find out the depth of hardness. So, whenever you complete the throughout hardness process, you will get that depth of hardness. Means up to which 50% martensite is produced. Distance from surface towards the center, up to which 50% martensite is produced. So there I told the concept used is case depth. So when I am carrying out surface hardening or case hardening, I have a limitation of case depth or this surface depth. So case hardening or surface hardening, as per the requirement, you cannot imagine the case depth up to precise level of 0.1 millimeter can also be obtained. Is my requirement only 0.1 mm case depth. I don't want 1 mm or more than that, only 0.1 mm. Or my requirement is 2.8 mm case depth, not only 3, 2.8 only. So such precise case depths can be obtained by using different furnaces which have controlled parameters. Okay, so first let us understand what is the case hardening. So you might be remembering I told there are a number of types of hardening processes. How to make part hard. This is interview question. Very vague question may be asked. Tell me the types of hardening. How can you make the part hard? So number of processes are there. What we have studied in this chapter, these are conventional hardening methods. Means conventional hardening consists of heating, soaking, and quenching. Then in the conventional hardening, some similar, it's other types of hardening also covered. That is stage quenching, os tempering, mark tempering. These are also types of hardening, but it consists of heating, soaking, and cooling, and making the part thoroughly hard. One more similar method which consists of heating, soaking, cooling is case hardening, surface hardening. One more method I told, precipitation hardening. You can make the part hard by formation of precipitation, but it is applicable to only particular alloys. One more method, dispersion hardening or strength hardening. Then solid solution strengthening I told during effect of falling elements. And one simple method I told, cold working process. If you take any steel plate, if you measure the hardness, suppose it gives a 15 RC, and if you roll it 5-10 times, that 15 RC becomes 18 RC. Because of deformation of the grains, hardness increases. So these are the number of ways by which you can make the part hard. This is the interview question I told, you can write it somewhere. Now, case hardening process consists of hardening the part up to particular depth as per the requirement. This process is cheaper or economical, we can say, than through hardness process. Hello? Am I audible? Through hardness process consists of unwanted area get hardened. And in that case, shock absorption capacity is less. So to overcome it, only surface is made hard and center kept tough as it is by perlite, whatever initial composition as it is. This process is divided into two types, by changing the phase and by changing the chemical composition. Okay. Before I explain you the types, write down the definition. Case hardening, underline dash, case hardening or surface hardening. It is defined as process of hardening in which so you remove the word it is defined as, directly write it is the process of hardening in which it is the process of hardening in which surface is made hard. Surface is made hard by changing chemistry of surface or by changing phase at the surface. Keeping center tough. I repeat once again. It is the process of hardening in which surface is made hard by changing the chemistry of surface or by changing the phase of the surface by keeping center tough. TOUGH, tough. Next line, what are the types? First, right? Right. By changing the chemistry. Chemistry means chemical composition. Carburizing. Cyaniding. Nitriding. Carbonitriding. So by changing the chemistry, carburizing, cyaniding, nitriding, and carbonitriding. These are the four types of case hardening process by changing the chemistry. So carburizing is again further divided into solid, liquid, and gas carburetor. Second is by changing the phase at surface. First is flame hardening. Second is induction hardening. So by changing the phase at the surface is flame hardening and induction hardening. So usually this will be treated as a surface hardening and this will be treated as a case hardening, but meaning is same for both. But when we are using the terminologies, case hardening means usually carbonizing, cyaniding, nitriding, carbonitriding, and surface hardening terminology is used for flame hardening and induction hardening. INDUCTION. So let us see one by one. Today we will see this part B first and then part A. Or you can write A this and B this. You can make this A and this as a B. So A by changing phase at the surface. Pay attention. Our aim is to make the part hard, surface of the part hard. So there are many applications where I told there will be matting surfaces, means combination of two different parts. And because of that matting areas, there will be wear and tear. To avoid wear and tear, the surface is made hard by one of the technique called as flame hardening. Flame means there is a heat. With the help of flame, you are going to make the part red hot. In the furnace, you are keeping to make it red hot. In the same way, you are going to take the flame, the gas flame, oil flame, whatever may be. And if your area is larger, you are supposed to hold the flame over the length or over the width. And then, once you heat that, you have to check whether it will be achieved up to red hot temperature, and after confirmation of the temperature, whether it is in the austenitic zone, immediately that part is cooled or quenched with the help of water or oil. So bottom line, when you are going to heat the component to the austenitic zone, initial phase, suppose this is perlite. Now this complete part is of perlite, and I will take the gas flame and I will hold it here. When I will hold it here, this area will become red hot, means phase change. That's why classification is made by changing the phase. Initial phase is different, and after heating, phase becomes austenite, and immediately after cooling, it becomes martensite. So complete, it is a perlite, and now assume that this upper white border you are observing. So this is heated and cooled, remaining perlite as it is, and upper is martensite. Just imagine, for your understanding I am telling. So this surface becomes hard. So on this surface you can use any other matting surface, and it will not get wear and tear. Okay. So this flame hardening is carried out as per the requirement. So first is spot method. Spot method means, suppose this is complete part and there are 3-4 matting parts. 1, 2, third maybe here. So in that case, suppose it is rotating in this way, or it may be just moving in this way, not complete area is covered. So in that case, why to make complete long 1 meter, 2 meter part hard? Only small area is to be made hard. Just it is called as a spot hardening. Hold your flame on that area for sufficient time. It will become red hot and quench immediately. Only that area will be converted into martensite. I hope you are understanding. So that is spot method. Second is progressive. Now, for example, this is one part, and I want to make this complete surface hard. In that case, either flame is to be moved or this part is to be moved. Okay, feed is given FWD, either to flame or to workpiece. What you are getting from this figure? Hello? Am I audible? Hello? Am I audible?
Yes, sir, audible.
Okay. So what you are getting from this figure? So in this case, this part is moved upside. So first you will come in contact with fire, and then it will come in contact with coolant. First it will come in contact with fire, it becomes red hot, and then it will come in contact with coolant. And in this way, this part is already hard. Hatched area shows that that part has become hard, and this part yet to come in contact with coolant, and then it will become hard. So this is called as a progressive method. Either this flame is moved in this way, or flame is constant and workpiece is moved in this way. I hope you are getting. Draw this figure. Or please reply. Or reply somebody whether
Yes,
figure
sir.
is over.
Yes, sir.
Okay. Now, so progressive method consists of, in suppose this is only flat part. Assume that this part is having some diameter. In that case, when it is having some diameter, the next method is called as spinning method. Spinning method. Spinning means and last one is combination. Spinning and combination. So assume that this part is 1 minute. I have this. There is problem in the laptop. Just few seconds. Okay. Am I audible? So this method I have explained. Spot method, only hitting at the spot and quenching. Second, progressive method, in which the part is either moving or flame and coolant is moving. Either part or workpiece is moving or flame and coolant is moving. It depends upon how feed you are providing. So immediate quenching is required, otherwise the part will get normalized. And in this way, the schematic diagram is drawn. Now, spinning means what? Part is round. So your flame is held in this way. And this is now 2D figure. It will rotate. So automatically, circumference will be covered. Okay. So part has given feed in the rotary direction and automatically circumference will be covered. And once temperature is achieved, quenching is provided. Combination method is completely, this is not only rotating but also moving in the feeding. So this final figure is important. You draw, aside the 4 types, and this is completely showing spinning as well as progression method. You can add this as a feed. FWD. Okay, draw this figure. This is asked only for 3 marks or 4 marks maximumly in the short note. What is flame hardening? What are the types and what is the working? Okay, in this way, and the applications may also be asked. I told some machine beds where there are reciprocating parts and you make 2 surface hard. Second type is important, induction hardening. May I erase this? May I erase this?
Yes, sir.
Now, word induction, recall where we have used. Many times we are using this word induction. In second year, in manufacturing process also, there was induction furnace. Try to understand the concept first. Very simple thing. It is working on the principle of induction. What is principle of induction? When primary current is passed to when current is passed to the primary coil, secondary current generates into the core or for which the coil is or wire is wounded. Now, based on this principle, you know that same principle used in induction furnace for melting the components. The wires were wounded around the furnace. Secondary, in that case, it was charge. Okay, and that charge used to melt. Here, we are not going to melt anything, just heating. heating the part up to the austenitic zone. Now, one limitation to this process than flame hardening. Flame hardening, there is no limitation of size, there is no limitation of shape, but induction hardening have limitation of size and shape. Because you are going to wind the coil and you are going to pass the high frequency alternative current. When high frequency alternative current is passed through that coil, whatever component or specimen you have kept and coil you have winded, suppose this is your component and this is a coil. Assume my finger as a coil and it's round. High frequency alternative current is passed through it. And then EMF is induced, secondary current induced in this, and this is called as skin effect. That EMF or secondary current moves only at the surface of the component. Higher the frequency of alternative current, this current, which is a secondary current, which is moving along this component, it will be on the upper and upper side of the surface. That's why it is called as skin effect. So if frequency of alternative current is less, the current movement will be up to the core. And if current movement will be up to the core, part will be heated up to the core. That we don't want. Suppose this is one of the part where I want to make only surface hard. And only thin layer of surface is to be hard. That's why depth of hardness is inversely proportional to square root of frequency. Make underline or square bracket to this formula. D is nothing but depth of hardness. It is inversely proportional to square root of frequency of alternative current. Higher the frequency of alternative current, smaller the depth, precise the depth you can achieve. If frequency of alternative current is less, you will obtain more depth. That we don't want. Okay. Now, how it works? It is, see, once I will explain this, you can do this experiment as a mini project. In T, you are having mini project. Anybody of you can select this. Now, in this case, simple table is used. On this table, the arrangement is there. Coil is kept in this way. And operator, which is working within a few minutes, he is having two bins. Two bins means two racks are there. In this left hand side, the part which is supposed to be hardened, and right hand side, he will keep the part, finish the part. Okay. Hold the part here. In this way. And there are two buttons. One is current on, another is coolant on. So first he will make current on, and coil which is winded or this specimen is kept in between the coil. This is a hollow coil. It is a pipe actually, and current will pass through it. High frequency alternative current is passed, and if you see from the top side, so I will not draw this head to the component. This is your component. If you see from the top, you will find the red ring, like eclipse. सूर्यग्रहणाला कशी दिसते, red ring तशी दिसते. So you can observe red ring means outer surface becomes red hot. Once the time is set, once the sufficient temperature is achieved, coolant on. I repeat once again, once that particular temperature is achieved, immediately current off and coolant on. Why this very fast process is there? Because we are not permitting any normalizing. There is no time for removing this part and again putting in the quenching. By that time, some of the surface becomes perlite. So to avoid it, only within fraction of second, the coil itself are hollow and provided with holes from inside. As soon as we'll make coolant on, coolant will come and fall on this surface and it becomes, or it will get cool. Automatically, only surface becomes hard because heat, we have not given time for heat to reach inside the core. Otherwise, if frequency of alternative current is less because of conduction, because it is metal, your part will take more time for heat. We don't want that. Only due to skin effect, the surface becomes red hot and we get, that part gets cooled immediately. So this is working on induction principle. You can make, or you can use this as a mini project model and you can make the part, you have to design the coil accordingly. This coil is fixed for this component. If component size is larger, coil size will be larger. Then tell me what is limitation. What is limitation? Very simple. Size is limitation. Can't put very big part. If you put very big part, that much big coil is required for it. And second limitation? Tell me second limitation. What is the second limitation? Any idea?
Diameter.
Not diameter. I already told that. Size already I told. It covers diameter. In the terms of shape, symmetrical shape is required. Non-symmetrical shape, how can you keep in the winding area? So part must be of little less size and part must be symmetrical. And in this way, we can achieve the desired depth of hardness. If case number 1, I got depth of hardness D equal to 0.5 mm. So I want to increase the case depth to 0.6. In that case, I will decrease the frequency. So there is some complete model is there. If I want 0.1 mm case depth, I have to increase the case depth. Increase the frequency. Higher will be the frequency, lesser will be the case depth. Are you getting my point? In this way, the depth of hardening is achieved as per the requirement. And this process is called as induction hardening process. Okay, I've done something. Now, I think you have written for flame hardening. Types you have written. And below it you write, flame hardening can be carried out for any size of the components. Flame hardening can be carried out for निशा सर मला सारखं फोन करायले जर काहीतरी इमर्जन्सी वाटतं माझं लेक्चर सुरू आहे त्यांना लावा फोन लेक्चर सुरू आहे सांगा त्यांना वाच sorry there was some emergency So you have written flame hardening. Flame hardening is carried out for making surfaces hard by heating the surface with the help of flame. So the desired temperature is achieved. The desired temperature is achieved to obtain austenite phase. And then it is quenched to obtain martensite. Full stop. There is no size limitation. There is no size limitation. And depending upon it, that is size. Different methods are adapted as given above. That is spot, progressive, spinning, and combination. Make star mark. Make star mark and write, there is no close control over the case depth. This is important statement because it may be asked in the MCQs or oral. It may also be asked in the interviews, which are the methods which use precise case depth. Flame hardening, you are taking the flame and you are heating. So there is no control over the case depth. So make star mark and write, there is no close control over the case depth. Next line, write induction hardening. It is working on the principle of induction. It is working on the principle of induction. Full stop. Next line. High frequency alternative current. High frequency alternative current is passed through the coil. Which is winded. Which is winded. Which is winded around the specimen. Around the specimen. Full stop. This high frequency alternative current will produce secondary current. Secondary current in the surface of specimen. in the surface of specimen. Full stop. This current moves on the surface with skin effect. This surface moves, this current moves on the surface of specimen with skin effect or due to skin effect. Full stop. Lesser the frequency of alternative current, lesser the frequency of alternative current, comma, the current may go inside the surface. The current may go inside the surface to heat it thoroughly. To heat it thoroughly. Full stop. Hence, to achieve minimum case depth, frequency of alternative current is kept higher. Next line add-on. Depth of hardness is inversely proportional to square root of frequency of alternative current. Depth of hardness is inversely proportional to square root of frequency of alternative current. Next line. As soon as the surface becomes red hot, comma, the current is of OFF. And coolant is sprayed through the same hollow coil. Coolant is sprayed through the same hollow coil to avoid the delay in quenching. Full stop. Surface is converted into martensite. Phase of the surface is converted into martensite. Full stop. This process has limitation of size and shape. This process has limitation of size and shape. Maybe 2 feet, 3 feet diameter, up to that you can do it. But 2 meter size part, difficult, because again cost of coiling etc. will be increased. And shape must be symmetrical. Next line, make star mark. It is having close control over the case depth. It is giving close control over the case depth. So I have shown this top view here. You'll observe this red ring, red hot surface. This way you can draw both the figures. Strength is very poor today. I don't know what is the reason. They have missed the important concept of flame hardening and induction hardening. So both the methods, friends, are of type A, where it consists of making the part hard by changing the phase at the surface. So initial complete part was of perlite or maybe any other phase, and now only surface becomes martensite. Okay, so this is the type in which the surface of the part is converted into the hard phase martensite, and then we have achieved the desired hardness of the surface. A short note may be asked or sub question may be asked. What is principle of induction hardening? Explain the mechanism with net sketch. This is schematic diagram sufficient. Okay, only good quality you draw in the notebook, and only it may be asked a short note induction hardening. So you have to explain everything. This is important. This is also asked in the MCQs. Depth of hardness is inversely proportional to square root of frequency. Following method have close control over the case depth. MCQ. So another methods also given, and the method which don't have close control, its names are also given. You have to find out which method have close control over the case depth. So if induction hardening and flame hardening are considered, flame hardening does not have close control, whereas induction hardening, you can just change the knob of frequency and you can change the depth of hardness. Okay, this is all about induction hardening and flame hardening, and in the next tomorrow's class we are going to see case hardening methods by changing the chemistry. We are going to stop here today. Okay, thank you.